Welcome back to the Explainer, everyone. When you look at a modern server farm today, you just see rows and rows of cold, hard silicon chips. There's this baseline expectation of physical permanence, right? We naturally just assume that the foundation of our entire digital age is totally indestructible. But as we unpack the source material today and really dive deep into the foundational tech of the 1940s, well, that image of solid permanence completely shatters. Because the absolute engine that powered the most heavily mechanized war in human history, it wasn't made of robust silicon. It was incredibly built on a fragile, glowing glass bulb housing this chaotic storm of boiling electrons.
Okay, let's dive into this, because it presents an almost impossible paradox when you stop and think about it. How on earth did a delicate vacuum tube, something that is quite literally just comprised of thin glass and highly sensitive internal wire, get violently forced by the extreme unforgiving conditions of World War II to effectively birth the modern digital age? I mean, how does something so inherently easy to break survive in the most hostile environments imaginable? Well, to answer that, we're going to have to look really closely at the microphysics. We need to see what's actually happening on the inside of that glass envelope.
So, let's get into part one, inside the glass valve.
The source material gives us this really brilliant analogy to start with. A vacuum tube essentially acts as an electrical valve. Think of it like a microscopic gate. Its entire purpose in life is to perfectly control an invisible stream of electrical current. It can turn that stream on, it can shut it off, or it can amplify it. Now, sure, that sounds super simple on paper, but actually creating that microscopic gate, that requires an absolutely insane amount of internal engineering.
The internal mechanics have to operate sequentially. Step 1, you have to heat up a tiny metal filament inside the glass until it literally, and I mean literally, boils off electrons. Then, step 2, you introduce a secondary wire grid to control that specific flow of electrons. But step 3 is where the real headache lies. To control that invisible stream without any interference, you have to completely pump the air out of the glass to achieve extreme vacuum levels. We're talking down to nanopascals. To put that into perspective for you, that is an internal environment emptier than deep space. Plus, all these components required utilizing ultra-pure, rare metals. Because of all this crazy complexity, a nation's ability to mass-produce these delicate little valves became a direct proxy for its sheer industrial power.
Moving right along to Section 2, Extreme Internal Modifications. The source highlights this massive divergence in how different nations approach this tech under wartime pressure. The Allies? They utilized extreme standardization, the right TMA standardization system. They essentially had an unlimited bucket of highly specialized Lego bricks. If a radar needed a very specific frequency switch, boom, a factory turned out thousands of a specific tube designed for that one exact job. But Germany was operating under a total starvation economy because of global blockades. They just couldn't afford a massive catalog of specialized parts. So they engineered the RV12 P2000. It wasn't a specialized Lego brick, it was a Swiss Army knife. By just altering the external circuits around it, their engineers could force this single standardized tube to act as a radio receiver, an amplifier, or even a logic controller in a V2 ballistic missile. It was one physical design forced to adapt to whatever the heck was needed.
Now, what's really interesting here is this machine, Sigley. This was the unbreakable transatlantic voice scrambler used by Winston Churchill. And this thing was an absolute beast. It weighed 50,000 kilograms and chewed through 30 kilowatts of power. Its sole purpose? To digitize voice data using something called quantum random noise.
And this gets directly into the incredible physics inside the tube. You see, the vacuum tube doesn't just pass a clean current. It's actually capable of capturing the random, chaotic movement of electrons bouncing around inside the vacuum. That chaotic electrical hiss is literally quantum noise. So Sigley took Churchill's voice, converted into electrical signals, and mixed it with that totally unpredictable internal electron hiss. Anyone trying to listen in? They'd hear nothing but static. But the receiver on the other side had a perfectly synchronized copy of that exact hiss and mathematically subtracted it out, revealing the clean voice. They weren't just passing currents anymore. They were mathematically weaponizing the unpredictable, chaotic atomic environment inside the tube. Mind-blowing, right?
So let's see how this builds into an entirely different set of extremes. We go from a 50,000 kilogram building-sized machine to the complete opposite physical spectrum, the proximity fuse. The goal here was to miniaturize a radar station so it could fit inside the nose of a naval artillery shell. But the challenge is just staggering. How on earth do you fire a fragile glass bulb out of a cannon at 20,000 Gs of acceleration without it instantly turning into completely useless dust?
Well, to survive that, engineers had to fundamentally redesign both the internal and external architecture of the tube. As detailed in the source, they completely reworked the inside first. They dramatically shortened the internal wires so they simply couldn't flex and snap under that incredible G-force. Then, they addressed the exterior by suspending the glass envelope inside a rubber casing. And finally, this is my favorite part, they filled all the empty space in the nose of the shell with a dense wax potting compound. This dense wax actively absorbed the shockwave of the cannon launch, preventing the glass from shattering. They literally packed a highly sensitive glass radar station in dense wax and fired it out of a cannon. And incredibly, it actually worked. No way, right? But it did.
Which brings us to Section 3, the thermal breaking point. The sheer volume of tubes required for early computing was an absolute logistical nightmare. Just look at the ENIAC computer. It weighed 30 tons and required a staggering 18,000 vacuum tubes working simultaneously just to operate.
And this creates massive narrative tension, right? Because as we've learned, you have 18,000 individual glass bulbs, all heating up tiny internal metal filaments to physically boil off electrons. The immense heat generated by 18,000 glowing bulbs in one single room is astronomical. It begs the immediate question, how do you keep an operation like this running without the entire system literally melting down into a puddle?
Well, the operators came up with a brilliant yet totally counterintuitive workaround, as the source text reveals, deliberate undervolting. Instead of giving the tubes the power they were designed for, operators fed them less electricity than they were officially rated for. They had intentionally starved their multi-million-dollar supercomputer of power. But why? So the crucial point is, it was entirely about managing internal thermal stress. Think about a regular light bulb burning out the exact moment you flip the switch. Every time you turn a tube on, the sudden spike in temperature heavily stresses the metal filament inside. By permanently running them at a lower voltage, step 1, the filament runs cooler. Because it's cooler, step 2, the internal metal expands and contracts far less violently during operation. And step 3, this deliberate mitigation of thermal stress exponentially increases the physical lifespan of the tube. They saved the hardware by holding it back.
But, undervolting was just a band-aid. The inherent physical fragility and the massive, unmanageable heat generated by the vacuum tube umpire pushed the technology to its absolute breaking point. It was this exact wall, this severe thermal and physical limit, that directly drove researchers at places like Bell Labs to invent a fundamentally better way. This culmination of pressure directly led to 1947, when Bell Labs invented the solid-state transistor. It's incredible to see these two eras contrasted. The hollow state, defined by boiling electrons in fragile glass vacuums, was suddenly facing the solid state. Transistors did the exact same electrical valve job as the vacuum tube, but they used solid semiconductor materials. There were no boiling electrons, there was no fragile glass to shatter. The vacuum tube empire that practically won the war was rendered virtually obsolete almost overnight. The crushing pressures of global conflict forced a delicate glass technology to its absolute limit, and in doing so effectively forced the birth of the robust, solid-state digital age that you and I rely on every single day.
Which leaves us with a truly fascinating idea to mull over as we wrap up this explainer. We just saw how the immense, crushing global pressure of a world war was required to force the fragile glass bulb to birth the modern digital era. So, as you look around at the world right now, it kind of makes you wonder, what massive global pressures today are quietly forcing the creation of the foundational technology for the next century? Food for thought. Thanks for joining us, and we'll catch you on the next one.